So today we're starting our discussion of the Freely algebra. And we did cover this before from Sarah, but I feel like Bourbaki outsources a lot of the setup, so it's kind of a good thing for us in this case. So we're going to start out with a revision of free algebras. So we're going to let X be a set with a free magma, which we have seen before, and we're writing this here as M of X. Mx with the strings of length n being our strings of length n are non-commutative strings, I guess non-associative strings. So it could be xn. Component is probably the wrong word, but you know what I mean. So we're going to let W and W prime be in Mx with integers p and q such that W lies in xp, and W prime is in xq. So essentially this is how many elements generate each of these. Then we know that the product under the magma of W prime is going to be inside X of P plus Q. If we let n be P plus Q, you forget this, and we can generalize that to your product on the entire free magma. And we have this is universal, as we want every mapping of X into M for some magma M has a unique extension to magma homomorphism from the free magma of X into M. And recall here we have L denoting the length, and we recall that decomposition of elements of the length at least 2 into a product is unique in a magma. Now we can write that down, just throwing that out there. The algebra of the magma Mx with coefficients in K is here written, is here denoted as LIB, potentially K of X. I don't know what lib is supposed to stand for. In this case, Mx is a basis of libx is a K module, so X is identified with a subset. And if A is an algebra, every mapping from X into A has a unique extension to a homomorphism, an algebra homomorphism, of course, of the free algebra into A. A little bit more of a reminder here. Work. I don't know what's that called. There's a word I'm trying to think of. A bit more review here. Constructing the free Lie algebra in this manner. Definition. The free Lie algebra over the set X is the quotient algebra of Lx being the free algebra of X divided by A, where A is the two-sided ideal of the free algebra of X generated by elements of the form. First off, we have Q of A times A and then we have the Jacobian, of course. That's giving us our, what is it called? Alternativity. That's why I always use anti-symmetry. And we have that our Lie brackets are going to be 0. Okay, so we have that L of X now is clearly a Lie K algebra. The composition of two elements is denoted the Lie brackets. Next important part is proposition. Let phi from the free algebra of X to the free Lie algebra of X be the canonical mapping, which is, the quotient map. And we're going to let phi be the restriction of C2X. So essentially this is going to give us our image of the elements of X inside of the free Lie algebra. For every mapping f of X into a Lie algebra G for G a Lie algebra, there exists a unique homomorphism F from Lx. The G is a homomorphism such that little f is the image of capital F on phi. Proof existence of F, of course. Let H be the homomorphism of the free algebra of X into G, extending F. For all A in the free algebra, H of Q of A, which as we recall is A dot A times A, which I guess is just the next part of our equation, is the bracket of H of A with itself is 0. With H of the Jacobian identity of A, B, and C 0 similarly. Thus H of our ideal A is 0, where A is the ideal above. I didn't notice they doubled that notation again. Don't know why they like doing that. So there is a homomorphism F of the free Lie algebra of X into G. They're really getting at it upstairs today. Such that H is the composition of F and C. We are done after restricting to X. Now, uniqueness. Now we're going to let F prime be another Lx to G such that F is the composition of F prime with phi. The homomorphisms of F of psi and F prime of psi of the free algebra of X into G coincide on X and hence are equal as C is surjective. We get that F is equal to F prime. And this comes with a corollary. that the image of our x in the free Lie algebra is free over our base field ring, whatever that's going to be, in the free Lie algebra. Proof. Let x1 through xn in x be distinct, of course. Distinct. And lambda 1 through lambda n in k such that the sum of lambda I phi of xi for 1 through n is 0. Let G be the commutative Lie algebra with module k. So essentially we're just taking k, we're taping onto it this zero Lie bracket. Then there exists a homomorphism Fi of Lx into G such that Fi of the image of xi in the free Lie algebra is 1. This is, this is a better way to write it. Fi of phi of xj is going to be delta of ij, so this is 1 if they match, and 0 if they don't. Applying this to the sum of lambda I phi xi equals 0, we get that each lambda I is 0. Alright, so corollary. Let A be a Lie algebra. Every extension of the free Lie algebra by A is an essential. Proof. Take the extension given by lambda of A into G and mu of G into the free algebra on X. This is an extension. As mu is surjective, there exists a mapping F of X into G such that phi is the composition of mu on F. Let capital F be the homomorphism of the free Lie algebra of G, free Lie algebra of X into G, such that little f is the capital F acting on phi. And then mu of big F of phi is mu on little f is phi so that mu of big F is the identity of the free Lie algebra. And so the extension is an essential. And a quick note on this: as k is non-zero, our first corollary here shows that phi is injective. Phi is injective. So we can identify X with its image in L of X. With this convention, X generates L of X, and every mapping of X into a Lie algebra G, for G being a Lie algebra, can be extended to a Lie algebra homomorphism of Lx into G. Alright, remark. When X is empty, Mx is empty, and so L of X, the free magma is empty, so L of X is just a 0. If X is a single element X, the submodule of K scaling X of L of X is a Lie subalgebra of Lx. As X generates L of X, the free Lie algebra of X, we have that the free Lie algebra of X is a free module with our basis of just that generating element. Alright. Next up we have our next chapter is presentations of Lie algebras. So a lot of noise happening always. Let G be a Lie algebra and A be a collection of elements AI, be a family of elements in G. we're going to let FA be the homomorphism of the Freely algebra of I of our into G, mapping each. Oh, this is the I is our indexing set of A. I'll write that here. So FA is a homomorphism of the Freely algebra of the indexing set, mapping each I to the corresponding element in A. So it's mapping inside of G, essentially. Yeah, it is. We said that already. My brain is fried. The image of FA is the subalgebra of G generated by A with the elements of the kernel of FA are called the relators of A. A is called generating, or alternatively free, or alternatively basic. If FA is surjective, it's generating. If it's free, then FA is injective. If it's basic, FA is bijective. Alright. Alright. Let G be a Lie algebra. Let G be a Lie algebra. A presentation of G is an ordered pair of A and R consisting of a generating family A being a collection of AI indexed with an indexing set as above, and a family R being equal to RJ indexed by a second indexing set of relators of A. Generating the ideal of Li of the free algebra of I as the kernel of FA. And we also say that G is presented by the family A related by the relators Rj for j and j. Now let I be a set, and R being a collection as above of j and j, a family of elements of the free Lie algebra of the indexing set. Let A sub R be the ideal of Li generated by the R through an L of I comma R, which is the quotient of the free Lie algebra of the indexing set by the ideal generated by R, is called the Lie algebra defined by I and the family of relators are j for j and j, we also say L of I and R is defined by the presentation of I and R, or also by I semicolon Rj equals 0 for each j and j. When R is empty, then the presented Lie algebra is just the free algebra on the indexing set. Alright, so I and R is above. Let Ci be the image of I in the in the algebra of I related by R. The generating family Xi of elements Xi in our indexing set be the generating family I and the family of relators R constitute a presentation of L of I related by R. Conversely, if G is a Lie algebra and AR is a presentation of G. Sorry, there's going to be a lot of weird noises in this video. There exists a unique isomorphism of LIR into G such that U of CI is AI for all I in I. Alright. Next chapter might be the last one for today, might not be. Is on Lie polynomials and substitutions. So we're going to take I be a set, presumably we can index something. We're going to let T, I be the image, the canonical image of I in the canonical image of I in Li, which can also be denoted as L of Ti for I in I. The elements of L of I are called Lie polynomials and the indeterminates of Ti indexed by I. Let G be a Lie algebra. If T, the family of Ti, be elements of G, the family of elements of G, let Ft denote the homomorphism of Li into G such that Ft of the ith indeterminate is Ti for I in our indexing set. The image under Ft of the element P of Li is sometimes denoted by P of Ti for I in the indexing set. In particular, we have that P of our indeterminates is P with the above element P for our little Ti's being the element of G obtained by substituting our elements for our indeterminates in the Lie polynomial. Let sigma be a Lie algebra homomorphism from G to G prime. For each family of elements Ti in G, and all P in the free Lie algebra indexed by I, we have sigma of P of Ti indexed by I is P of sigma of Ti indexed by I as phi acting as sigma acting on phi ft maps Ti to sigma of T little ti. Let Qj for j and j be elements of the free Lie algebra indexed by I. Let P be in Lj. By substituting the Qj for the Tj in P, we obtain a Lie polynomial R be P of Qj for j in J, which is in Li. Then R of Ti for I in I is P of Qj. These brackets are really getting messy here. Ti for I in I for j in J. For each T being a family of elements in G, and I being elements of G, as seen by the homomorphism, operating the homomorphism Ft on the equation R equals P of Qj for j in J. Let G be a Lie algebra, I be a finite set, and P be a polynomial in the free Lie algebra. Now suppose G is a free as a key module, then the mapping P tilde of G to the I and G as P tilde of our collection of Ti is equal to just P. Similarly, is then a polynomial. For the set F of mappings of I copies of G into G is a Lie algebra with bracket being the bracket of phi and psi of t. I should write this on a new line. The bracket of phi and psi on t is the bracket of phi on t and psi on t. With the set F prime of polynomial mappings of gi into g is a Lie subalgebra of F by bilinearity. Our assertion follows from the fact that mapping from P to P tilde is a Lie algebra homomorphism. Lie algebra homomorphism that Ti is PR and that Ti tilde, the notation gets weird here, is Pri in F prime for all I. Alright, and let's go on to functorial properties. I know we're going to go a bit long, but I think it's kind of for the best right now. Functorial properties. To be honest, there are people visiting my house upstairs, and I'm doing this to avoid interacting with them. Proposition. Let x and y be sets. Every mapping of just u from x to y can be extended uniquely to a Lie algebra homomorphism where L of u maps L of x into L of y. For each v from y to z, L of v composed with u is L of v composed with L of u. We know that LU is already going to exist. Proof is just the restriction of LV composed with LU to X is equal to the composition of LV with LU restricted to X, and so they are equal. Which comes with a corollary. If U is injective, surjective, bijective, so is the free Lie algebra of U. The free Lie homomorphism of U. And proof. We're going to assume X is empty, otherwise it's going to be trivial. U is the function from above. If U is injective, there exists a mapping V of Y into X such that V on U is the identity of X. Essentially you're stating that injectivity means you have a right inverse and V is such an inverse for U. So LV composed with LU is the identity of LX, so LU is injective. When U is surjective, there exists a mapping W of Y into X such that W is a right inverse of U. So once again we have that LU of LW is going to be the identity mapping on L of Y. Sorry, 1 second. So LU, of course, is going to be surjective. Now, I think this is discussion. It's not really labeled very well, but let X be a set with a subset S. We have from above that the canonical injection of S into X can be extended to an isomorphism alpha of LS onto the Lie subalgebra L prime S of Lx generated by S. And so we identify the two. Let S alpha for alpha in an indexing set be a right-directed family of subsets of X with union S. The relation of S alpha being inside of S beta implies, of course, that the free Lie algebra of S alpha is in the free Lie algebra of S beta. So the family of Lie subalgebras L S alpha is right-directed. Therefore, G is the union of, for alpha and I, of L S alpha. This is a Lie subalgebra of Lx. Because with the above identification, this is all happening within Lx. Then S is in G. So L of S is in G. And as L of S alpha is in LS, for all alpha and I, G is in LS. Hence, L of the union of S alpha is the union of L of S alpha. Applying the above, to the family of finite subsets of X, we see that every element of Lx so the form is of the form Px1 through xn, where P is a polynomial in n indeterminates, and each xi is an x. Now this brings us to a proposition. Let K prime be a non-zero commutative ring and U from K to K prime being a ring homomorphism. For every set X, there exists a unique Lie K prime algebra homomorphism V from Lk of X tensor K prime into the K prime free Lie algebra of X such that V of X tensor 1 is X for X in X. Also, you know what, I'm just gonna write it in a more intelligent way than they did. V is an isomorphism. And the proof, applying a previous proposition to G being Lk prime of X as a PK algebra. The mapping of X into G, mapping X to X of X into G, we get a K homomorphism of Lkx into Lk prime X giving a K prime homomorphism V of Lkx tensor K prime into Lk prime of X. This V is unique and an isomorphism as the ordered pair Lkx tensor K prime along with the mapping from X to X tensor 1 solves the same universal mapping problem as the ordered pair Lk prime of X along with this identity looking map. Comes a remark. Let H prime be a Lie K prime algebra, and H the Lie K algebra derived from H prime by restricting scalars. Restricting, there's a ring of scalars. If P is in Lk of x, define P tilde is mapped from hx to h, as we saw. And then we can immediately that P tilde is V of P tensor 1 tilde. And I think we'll call it there. Kind of over my normal time, but like I said, I wanted to draw this out a bit further as much as I could, so I've done that. Thanks for watching.